Welcome to the second of two videos on um, solubility and precipitation reactions. We finished the last video by defining what a precipitation reaction was, which is a reaction in which you mix two water-soluble ionic compounds together and one of the products is not soluble in water. And then we did some exercises on just basically saying that looking at phase labels looking at state labels to decide whether or not a compound was water soluble. So if it has an AQ next to it, it's soluble in water. If it has an S next to it, that means it's not soluble and it's a precipitate. But this now raises the question as we move forward, how would you know if a particular combination of water soluble ionic compounds is going to produce a precipitate? And there are really two options to answering that question. One is I might tell you in the problem, and that is certainly true. You'll get problems where the precipitate is already identified by the state label. But you might have to work it out for yourself. Which compound is a precipitate, if any? And so in order to do that, knowing a simple set of solubility rules will allow you to predict whether or not a particular reaction is a precipitation reaction and what the precipitate is. And so just as a general background, most ionic compounds are soluble in water, and we've talked about that's because they're hydrated by water molecules. The negative portion of water molecules helps to dissolve cations, and the positive portion of water molecules helps to dissolve anions. But some ions, when we combine them, form a compound that is not soluble in water, and it will drop out of solution as a solid. And so learning this limited set of solubility rules will help you out a lot. There are more complex solubility rules. I've tried to streamline them for this class, and I won't give you problems really that force you to know any more than what I'm going to teach you here in terms of solubility rules. These are a hierarchy, that is, the earlier rules take precedence over subsequent rules, and you'll see what I mean as I go through these. The first rule of solubility of ionic compounds is that all ionic compounds that have an alkali metal cation or an ammonium cation are always soluble. So if you ever see a sodium salt, a lithium salt, a potassium salt, an ammonium salt, it is always water soluble, and as far as you are concerned, without exception. Those are the cations that are always water soluble. What about anions? There are two anions you should learn that are always water soluble, and those are nitrate and acetate, which are two of the polyatomic ions that we learned earlier in the year. Anytime you see a compound that is a nitrate compound, anytime you see a compound that is an acetate compound, it will always be soluble in water without exception for this class. Rule number 3 and 4 then cover some things that are generally not soluble in water. Generally, compounds that have carbonate or phosphate anions are not soluble in water. The exceptions to that will be compounds that follow rule number 1. So for example, lithium carbonate or sodium carbonate or potassium carbonate is soluble in water because rule 1 takes precedence over rule 3. Lithium, sodium phosphate, ammonium phosphate, etc., they are soluble in water because rule 1 takes precedence over rule 3. Rule 4 covers some cations that are typically not soluble, and the two you need to know are silver and lead 2. They are insoluble except in cases in which you have a nitrate or an acetate. So silver nitrate is water soluble, lead acetate is water soluble because rule number 2 takes precedence over rule number 4. And then the last rule would be that generally compounds that contain halides, and halides are fluoride, chloride, bromide, or iodide, or the sulfate ion, they are generally going to be soluble in water. But if you have a silver salt or a lead salt of one of these things, then they are not. Now I have just essentially taken these 5 rules and cut and pasted them into a Word document and put them into Veracross. And so if you want to download that to just have as a reference while you're working on solubility problems, that would be useful to you. Well, why don't we try taking those solubility rules and applying them to a set of compounds and determining whether or not the compound is soluble in water. So there are 3 possible answers here. It's either going to be that the compound is soluble, or that the compound is insoluble in water, or that you, based on the rules, you don't know. So you can go ahead and turn the video off, write down answers for these 7 compounds, and then turn it back on and see how you did. Well, here come the answers. Number 1, sodium phosphate is water soluble because rule number 1 says anything that's got a sodium cation is water soluble. So the presence of the phosphate, that generally phosphates are insoluble, but we said that is subject to rule number 1. And rule number 1 says any sodium salt is always water soluble. Calcium chloride, number 2, it is water soluble because our last rule, number 5, said that halides are generally water soluble. The only exceptions that you need to know would be a lead halide or a silver halide. So calcium chloride is water soluble. Sodium hydroxide is water soluble because it has a sodium cation. Number 4, aluminum carbonate is not soluble in water. It is insoluble. Rule number 3 said carbonates are generally insoluble unless they have a ammonium or alkali metal cation. Aluminum is not ammonium or an alkali metal, therefore aluminum carbonate is insoluble. Number 5, zinc hydroxide, we don't know. I know, but you wouldn't be expected to know because none of those rules that we looked at on the previous slide address the issue of zinc or hydroxide, so we don't know. Lead chloride is insoluble because rule number 4 told us that lead compounds are generally insoluble. The only exceptions would be nitrates and acetates, and so lead 2 chloride is insoluble. And then silver nitrate is soluble because rule two tells us that all nitrates are water soluble. Again, you've got a list of these rules that I have posted in Veracross, and you can download that and use it as a reference. I encourage you to do that. Okay, well, now that we know some solubility rules, we can actually use them to try and predict whether a precipitation reaction is going to occur when we combine a particular set of water-soluble compounds. So let's try answering that question. Will a precipitate form when aqueous solutions of calcium chloride and sodium carbonate are mixed? And then a second question, will a precipitate form when aqueous solutions of sodium chloride and potassium sulfate are mixed? So go ahead and take a look at your solubility rules. This requires you to identify what the products of the reaction are going to be. You don't necessarily have to balance the equation at this point. You just need to identify what the products of the reaction are going to be, and then apply the solubility rules and see whether one of the products is not soluble in water or whether both of the products are water soluble. So go ahead and you can pause the video, do it for both of these examples, and then turn it back on. Well, the products of when I mix calcium chloride with sodium carbonate, the 2 possible products are sodium chloride and calcium carbonate. Remember, this is a double displacement reaction, so we're just swapping, keeping essentially. Well, in this case, you're keeping the cations constant. They can't combine with each other, and you're just swapping the anions. So the possibilities are sodium chloride and calcium carbonate. I went ahead and balanced the reaction in this case. We know that sodium chloride is water soluble because of rule number 1. It's got a sodium cation in it. Calcium carbonate is insoluble because carbonates are insoluble unless the cation is an alkali metal or ammonium. That is not the case with calcium. Therefore, calcium carbonate is insoluble, and this would be a precipitation reaction. Um, Let me just go back and show you what I did here. If I combine sodium chloride with potassium sulfate, my possible products would be sodium sulfate and potassium chloride. I've gone ahead and predicted those products and balanced the equation all in one fell swoop. Um, so let's take a look at our products. Potassium chloride contains a potassium cation, so it is water soluble. Sodium sulfate contains a sodium cation, so it is water soluble. So in this case, there would be no precipitate. So at this point, we've learned what a precipitation reaction is. We've learned to look at the state labels and figure out what's water soluble and what isn't. We have learned some solubility rules, and we have then put them into action to predict whether a particular combination of water soluble reactants will give us a precipitate as a product. Now, the next thing to do is to take that equation that we've written for a precipitation reaction and convert it into what we call an ionic equation. The equations that we have been writing so far, we call them molecular equations, and that may seem counterintuitive because these are all ionic compounds, right? But we are writing them in their associated form. In other words, remember back in the first video, we talked about how to take calcium chloride and write it as its dissociated ions. We haven't been doing that yet with these precipitation reactions. We're writing these formulas as if they were molecules, even though they are in fact ionic compounds. And so we use the term molecular equation to refer to this because it writes everything as if it were intact. So this would be the molecular equation for a precipitation reaction in which we get silver chloride as a precipitate. We would call this the molecular equation for combining calcium chloride with sodium carbonate to get a precipitate of calcium carbonate. In order to convert these into ionic equations, we're going to use that skill that we learned back in the first video, which is to take an aqueous ionic compound and dissociate it into its ions. And at this point, now remember when back here when we were predicting whether or not there was going to be a precipitate, I told you it wasn't necessary for you to balance these equations at this point, although I did balance them here. It was simply necessary for you to be able to correctly predict what the products would be. Now, when we go to write ionic equations, it is really important at this point that you have a balanced equation. So let's let me do an example of what I'm talking about. To go from a molecular equation for a precipitation reaction to an ionic equation for a precipitation reaction, I'm going to take every water soluble compound and I'm going to dissociate it into its ions, just like we did in the last video. So let's see. I'm going to start with the left-hand side. Silver nitrate is water soluble, therefore I'm going to dissociate it. 1 times 1 is 1 silver ion. 1 times 1 is 1 nitrate ion. Remember, when I say 1 times 1, I'm multiplying the coefficient by the subscript. 1 times 1 is 1 sodium ion. 1 times 1 is 1 chloride ion. I've now gone ahead and dissociated the entire left-hand side of this equation into its dissociated aqueous ions. Now, how about the right-hand side of the equation? For sodium nitrate, 1 times 1, 1 sodium ion, 1 times 1, 1 nitrate ion. For silver chloride, you'll notice I haven't dissociated it. Why didn't I dissociate this? Because it's not water soluble. We only dissociate things that have an AQ next to them, right? Silver chloride is not water soluble, and so it doesn't dissociate into ions when I put it into water. It just falls to the bottom of the container and sits there. And so that is an example of taking this particular equation and rewriting it as an ionic equation by dissociating all the water soluble compounds into their separate ions. Now you take a try at this. Here is the reaction for the precipitation of calcium carbonate from calcium chloride and sodium carbonate. Go ahead and switch this off. Can convert this molecular equation into an ionic equation by dissociating all the water-soluble compounds. You can go ahead and switch the video off for a moment and do that. Okay, let's go ahead and walk through this. So I'm going to start with the left-hand side of the equation. 1 times 1 is 1 calcium ion. 1 times 2 would be 2 moles of chloride ions. 1 times 2, 2 moles of sodium ions. 1 times 1, 1 mole of carbonate ions. So I've done the entire left-hand side. Recall that the reactants in a precipitation reaction are always going to be water soluble, and so you're always going to be dissociating the entire left-hand side. Now let's do the right-hand side. 2 times 1 gives me 1 sodium. 2 times 1 gives me 1 chloride. Recall that for the precipitate, we don't dissociate it because it's not water soluble, so it just comes down intact. I'm making that point with the square there. So this is the correct ionic equation for the combination of calcium chloride and sodium carbonate to give you sodium chloride plus a calcium carbonate precipitate. Okay, so let me just summarize what I just did. We start with a balanced molecular equation. That was what we did here. We started with a balanced molecular equation. We dissociated all of the water-soluble compounds into their ions, and we identified the water-soluble compounds by the AQ. And when we did that, I indicated the correct formula and charge of each. Calcium, because it's in group 2, is 2 plus. Sodium, because it's in group 1, is plus 1. Chloride, because it's in group 7, is minus 1. Carbonate is a polyatomic ion that we've learned. It has that formula. So I wrote the right formulas. I've got the correct coefficient in each case. If there was a subscript, I turned that into a coefficient. If there was a coefficient, that remained as a coefficient. And I wrote AQ after each one. If the ionic compound is water soluble, then the individual ions are water soluble. And then finally, anything that has an S after it, you just bring down unchanged, and you'll see that I did that. Calcium carbonate with the S just came down as calcium carbonate with the S. All right, we've defined precipitation reactions. We've learned how to identify a precipitate. We have learned how to turn that molecular version of the precipitation reaction into an ionic equation. Now, the last thing to do is to write what's called a net ionic equation. And a net ionic equation eliminates all ions that aren't actually participating in the reaction. And we refer to the ions that don't actually participate in the reaction as spectator ions. And so spectator ions are going to appear exactly the same on both sides of an ionic equation. That's because they aren't the ions that are actually participating in the reaction. So let me give you an example of this, and let's go back to that first example that we saw. Silver nitrates plus sodium chloride gives sodium nitrate plus silver chloride. I had already written this as a molecular precipitation reaction. A few slides ago, I showed you this is the example of how to write the ionic equation. Now we are going to identify the spectator ions. And we identify them, we can identify what they are because they appear exactly the same on both sides of the ionic equation. So let's just walk through and query each ion one at a time. Silver on the left-hand side is Ag+. Silver on the right-hand side is part of a solid precipitate. So it is not a spectator ion. Nitrate is NO3 minus aqueous on the left. It is also NO3 minus aqueous on the right. So nitrate is a spectator ion, and I'm indicating spectator ions here by putting boxes around them. Sodium is Na plus aqueous on the left. It is Na plus aqueous on the right-hand side of the equation. So it is also a spectator ion. Chloride is Cl minus on the left-hand side. It is part of the insoluble compound silver chloride on the right-hand side, so it is not a spectator ion. So in the case of this reaction, I have identified two spectator ions, nitrate and sodium. So now it's time for you to do this as a practice problem. Here's our other reaction, the calcium carbonate reaction. So the task here is for you to pause the video, identify the spectator ions in the ionic reaction below. Okay, let's see how you did. Remember, we're going to query these things one at a time. Calcium is Ca2 plus aqueous on the left, but it's part of a insoluble compound on the right, so it is not a spectator. Chloride, 2Cl minus aqueous on the left, 2Cl minus aqueous on the right-hand side of the equation, so it is a spectator. Sodium, 2Na plus aqueous on the left-hand side, 2Na plus aqueous on the right-hand side of the arrow, so it is a spectator. Carbonate, CO3 2 minus aqueous on the left, part of an insoluble precipitate on the right, so it is not a spectator. So now we have identified the spectator, successfully identified the spectator ions for that reaction. Okay, what can we say about spectator ions? They're always going to have the exact formula on each side of the equation. You can see that here. What's inside the green box in each case is identical in both cases. What's inside the red box in each case is identical for both. They're going to have the same charge on each side. They're going to have the same formula. They're going to have the same physical state. They're going to have the same coefficient. 2Cl minus aqueous, 2Cl minus aqueous, 2Na plus aqueous, 2Na plus aqueous. They're going to be exactly the same. And that's why, by the way, it is very important that you balance the equation, that you write a proper equation and then balance it correctly before you do this process. Okay, well, to get to the net ionic equation, we simply take the ionic equation and we remove the spectator ions. So let's go through this. Let's go through this example, the one we just did. We take this molecular equation. We write the ionic equation in which everything is dissociated except for the calcium carbonate. We've already identified the spectator ions as being chloride and sodium. Now, to write the net ionic equation, we just remove those spectator ions from the equation. And what do we get? Calcium 2 plus carbonate gives calcium carbonate. So this describes what is actually happening in the flask. When I combine calcium chloride in aqueous solution with sodium carbonate in aqueous solution, I get a precipitate of calcium carbonate. The sodium and the chloride are simply just kind of chaperones to get the calcium and the carbonate into solution. They don't participate in the reaction. The actual reaction that's occurring is calcium ions plus carbonate ions precipitating out as calcium carbonate. Okay, so take a stab at this. Here is the silver chloride precipitation reaction. Go ahead and pause the video and go through the entire process of writing the ionic equation, identifying the spectator ions, and then writing the net ionic equation. Okay, well, we've already done the first couple parts of this. The ionic equation is simply to dissociate the entire left-hand side, then to dissociate the sodium nitrate on the right-hand side because it's water soluble, but to bring the silver chloride down intact because it's a precipitate. We had previously, with this same equation, identified the spectator ions as being nitrate and sodium. Once again, everything inside the box has to be everything inside this box has to be exactly the same as everything inside this green box. NO3 minus aqueous, NO3 minus aqueous. Same with the red boxes, Na plus aqueous, Na plus aqueous. Now to write the net ionic equation, we're simply going to remove those spectator ions from the ionic equation. And the actual reaction that occurs when we mix silver nitrate and sodium chloride is that silver ions from the silver nitrate seek out chloride ions from the sodium chloride that precipitate out as silver chloride. That's the actual reaction that's occurring. The nitrate and the sodium are simply there to get the silver and the chloride into solution. but they don't participate in the actual reaction. Okay, so let me just summarize the steps to writing a net ionic equation. We're just about finished here. I've got a couple more practice problems for you to do, but we've gone through the whole process now. I'm going to write a balanced molecular equation. I'm going to identify any precipitate and assign state labels. Everything that's water soluble is going to get an AQ. Everything that is not water soluble, and in this case, it's just going to be one of the two products, will get an S. That would be the precipitate. I am going to take everything that has an AQ after it now and dissociate it into its ions to write the ionic equation. I'm going to identify the spectator ions. I'm going to cancel out the spectator ions and write the net ionic equation. Okay, couple of practice problems for you. I've got a reaction here that I have already written and balanced. So here is a balanced molecular equation. Your job is to identify the precipitate, write a net ionic equation by first writing an ionic equation, then identifying the spectator ions, and then canceling out the spectator ions to get the net ionic equation. So go ahead and pause the video and go through the entire sequence. Okay, let's see how we did. So the first thing to do is to identify the precipitate. So we're going to look at our two products here, sodium nitrate and aluminum carbonate. Sodium nitrate is soluble because of both rules 1 and 2. It contains sodium and nitrate, which are always soluble. Aluminum carbonate, one of the rules taught us that carbonates are not soluble in water unless the cation is ammonium or a group 1 metal, which is not the case with aluminum, and therefore aluminum carbonate is our precipitate. Once we've identified aluminum carbonate as the precipitate, we're going to go ahead and put state labels on the sodium nitrate and the aluminum carbonate. And so because sodium nitrate is water soluble, I put an AQ there. Because we've identified aluminum carbonate as our precipitate, I'm going to put an S for solid there. Now we go ahead and dissociate our ions to write the ionic equation. 3 times 2, 6 sodiums, 3 times 1, 3 carbonates, 2 times 1, 2 aluminums, 2 times 3, 6 nitrates. For the left-hand side, 6 times 1, 6 sodiums, 6 times 1, 6 nitrates. We bring down aluminum carbonate intact because it is a solid. We now go through and query our ions to see if they're spectator ions. 6 sodium plus aqueous, 6 sodium plus aqueous. That is a spectator ion. 3 carbonates, which are 3 carbonate aqueous, 3 carbonates in an insoluble compound. That is not a spectator. 2 aluminum 3s aqueous, 2 aluminums in an insoluble compound. So aluminum is not a spectator. 6 NO3 minus aqueous, 6 NO3 minus aqueous. That is a spectator. We remove the spectator ions, and for the sake of my own neatness, because you always write the cation before the anion, I brought everything down to write the net ionic equation, but I also just reversed the locations of aluminum and carbonate. 2 aluminum ions plus 3 carbonate ions give me a mole of insoluble aluminum carbonate. That is my net ionic equation. Last one, I'm asking you to do one more thing here, which is to complete and balance this. So predict the products, balance it, identify the precipitate, write the ionic equation, write the net ionic equation, go have some lunch. Okay, so go ahead and turn the video off, give this a shot, and then turn it back on. All right, well, lead acetate plus potassium chloride is going to give me lead chloride plus potassium acetate. So I have in one step here written the products and balanced it, which just meant putting a 2 in front of the potassium chloride and putting a 2 in front of the potassium acetate. Now I am going to apply my solubility rules. Lead salts are insoluble unless they have a nitrate or an acetate. Uh, because the anion here is chloride, I expect lead chloride to be insoluble in water. Potassium acetate is water soluble because of both rules 1 and 2. It contains potassium and it contains acetate. Therefore, lead chloride is my precipitate. Having done that, I can now assign state labels to my two products. Lead chloride is a solid, potassium acetate is aqueous. I now ionize my entire left-hand side because they're both water soluble. On the right-hand side, the lead chloride remains intact while the potassium acetate is ionized, dissociated. I identify my spectator ions as being acetate, 2 acetate aqueous, 2 acetate aqueous, 2 potassium aqueous, 2 potassium aqueous. The lead is an ion here and in an insoluble compound here. The chlorides are ions here, but in an insoluble compound here. I now remove my spectator ions to give the net ionic equation. A lead 2 cation plus 2 chloride anions gives me a mole of insoluble lead chloride. Well, thank you for persevering through this video, and there is a worksheet or two. I'm not sure if it's going to be one worksheet together or two separate on solubility and then net ionic equations, but they will be available to you soon. And thanks for watching.